Hello everyone. This video is titled Add and Subtract Radical Expressions, right, or Roots. Right, so in this video, I'm going to be going over several examples of adding and subtracting radical expressions. And all the examples, all the exercises I'm going to be doing in this video are taken directly from a free online textbook at openstax.org. It's their Intermediate Algebra 2nd edition text. And I'll be working on the exercises that don't have solutions. So just the even numbered ones. See, the odd numbered ones you can click on and it'll take you to the solutions for those. So I'm going to be working on the ones without solutions. So exercises 166 through 182. And again, just the even numbered problems, the ones without solutions. And in the video, I will be putting in the description, I'll be putting timestamps for each example I do, each exercise. So example 1 will be exercise 166, example 2, number 168, etc. And you can just click on the timestamp in the description if you wish to skip ahead to a specific problem. And then one other thing I would suggest you do as well is that when I start a new question, when I start a new example, pause the video and try to work on it yourself first before you watch me do it. Because if you're just watching me work on these things and not practicing yourself, chances are you're not going to be learning all that much. Right? Okay, so bringing up the first example, which is, as I've written here, I'm writing the exercise numbers underneath the problem numbers now. So example 1 is exercise number 166, and parts A, B, and C. And we're asked to, add and subtract here, add and subtract radical expressions, and simplify. Alright, so part A, we have a difference, a subtraction problem here. There's a minus sign. There's 7 times the square root of 2 in the first term, minus 3 times the square root of 2 in the second term. Now these are what would be considered like radicals, because both terms have the same index, right? They're both got a square root involved, and they have the same radicand, right? The expression underneath the root is the same. Both of these have the square root of 2, so they would consider these to be like radicals. And the way we combine these is just like if we were factoring, right? Just like if you were factoring polynomials. Both of these terms have a common factor, a common radical, or a like radical. So I could factor this out. Now what I'm going to do is a little different. I'm going to factor it out on the right side of the parentheses, which is totally fine. So you see how both of these terms have the square root of 2 in common. Right, so I factor out the square root of 2. And then what would be left over in parentheses here is 7 minus 3. But that can be totally simplified, right? 7 minus 3 is simply 4. So we have 4 times the square root of 2. Right? And there you go. And I'll put it in a box. This is the final result. The result of combining 7 square roots of 2 minus 3 square roots of 2. Right? You get 4 square roots of 2. And you see how very similar that was to polynomials. If you had 7x minus 3x, you'd have 4x. Right? It's very same, but instead of x, it's the square root of 2 here. Okay, and then the rest of this number 1 example is very similar. So part B, you have 7 times the cube root of p plus 2 times the cube root of p. So once again, these have like radicals, right? Cube root of p in both terms. So as I did with number 1 part A, I'm going to factor that out, right? They both have the cube root of p in common, but I'm going to factor it out on the right side, right? So got the cube root of p factored out, and what would be left over would be 7 plus 2. But this factor here, 7 plus 2, can be totally simplified, right? 7 plus 2 is simply 9. So we end up with 9 times the cube root of p. And it's really that easy. And that's as simplified as that gets, right? You can't simplify that cube root any further. All right, and part C, no different. All right? Look at both terms. You have 5 times the cube root of x minus 3 times the cube root of x again. Again, we have like radicals. You can factor that like radical out, right? Both these terms have the cube root of x in common. So I factor out the cube root of x, right? And then what's left over would be 5 minus 3. And what is 5 minus 3? That is 2. Right? So we end up with 2 times the cube root of x. Very, very simple stuff, I feel. All right, I'll circle that. Okay, wonderful. All right, so moving on. Number 2, which is exercise 168. Right, number 168. Pretty much the same thing. All right, nothing too crazy here. Nothing changing really. Part A, we're asked to add and simplify. Well, we have 4 times the square root of 5 plus 8 times the square root of 5 again. So these terms have like radicals as well. So I can factor that out. I'll factor out the square root of 5, and again I'm going to do it on the right, because all we're doing really is combining the coefficients of those radicals. Right? You probably noticed that in number 1. You keep that like radical, and then you're just combining the coefficients of the like radical. Right? What would be left over when I factor out the square root of 5 would be 4 plus 8. Right? And 4 plus 8 is 12. So we end up with 12 times the square root of 5. And the square root of 5, that's as simple as that gets. There are no factors of 5 that are perfect squares, so we're done. This ends up being equivalent to 12 times the square root of 5. Right, in part B, very similar. We have the cube root of m minus 4 times the cube root of m. So again, they have a like radical, these two terms, the cube root of m, both the same index, the same root and the same radicand. So again, I'll factor out this cube root of m that both terms share. And when you factor out the cube root of m, what would be left over? Well, there's nothing in front of this first cube root, which means technically there's a 1 there. You can always put times 1 and it doesn't change anything. So I end up with this factor of 1 minus 4, right, when I factor out the cube root of m. And 1 minus 4 is negative 3. So we end up here with negative 3 times the cube root of m. Right, and this should be as simple as that gets. Right, part C, same thing. Both terms have the square root of n in common. So I'm going to factor that out, and again I'll put it on the right. You could put it on the left, it doesn't matter, right? As long as you're factoring correctly. factor out the square root of n, and what's left over would be 1 plus 3. Right? 1 plus 3 would be the other factor. And 1 plus 3 is simply 4. Right? So we have 4 times the square root of n, and that's as simple as that gets. Alright, next question. Number 3 is corresponding to, exercise 170. Alright, number 170. Alright, so here, part A, now we have 3 terms, right? The sum of 3 terms. But notice they're all they all have a like radical. They all have the square root of 11b. Right? The square root of 11b are in all of these. So I'm going to factor that out. Right? Factor out the square root of 11b. And if you were to do that, what's left over would be 1 minus 5 plus 3. And we just combine those coefficients. 1 minus 5 plus 3 is negative 1. So we have negative 1, which you just write a minus sign. Negative 1 times the square root of 11b. And that's, again, as simple as this gets. Alright. In part B, no different. All 3 terms here being added or subtracted have a like radical, have a common radical, the 4th root of 11cd, right? Every single one of these terms has the 4th root of 11cd. So I shall factor this out. So we pull out the 4th root of 11cd, and if I do that, what's left over is 8 plus 5 minus 9. Right? The other factor is 8 plus 5, which is 13, minus 9 would be 4. So this simplifies to 4 times the 4th root of 11cd. Right? And that is, again, as simple as this gets. Great. Alright, the 4th example, 4th exercise, which corresponds to exercise 172. Same thing, alright, all these are pretty simple so far. We'll eventually get into examples where we don't have like radicals, and then we have to do some simplifying of radicals before we can add or subtract. Okay, so once again here, every single term in part A has this like radical, common radical of the square root of 5d. So first I'll factor that out. Factor out the square root of 5d. And what would, the other factor after you do that would be 3 plus 8 minus 11. But 3 plus 8 minus 11 is just 0. So you'd have 0 times the square root of 5d, but remember 0 times anything is just 0, so this results in just simplifying to the number 0. Okay? Great. Then part B, same thing, all 3 terms have the common radical, have a like radical, the cube root of 2rs. So I shall factor this out. So one factor here, and then pull out the cube root of 2rs. And if I remove the cube root of 2rs, the other factor would be 11 minus 9 plus 3. But this simplifies, right? 11 minus 9 is 2, plus 3 is 5, right? So we end up here with 5 times the cube root of 2rs. Very, very simple. Alright, so the first 4 examples, the first 4 questions here in all the parts, every term had a like radical. that I could factor out and then very easily simplify. The remaining questions start off without like radicals, right? The terms don't have like radicals, and we have to do some sort of simplification of radicals to make them like radicals. Let me show you what I mean. All right, so here, number 5, which is exercise 174. Part A, we have, see, the square root of 72 minus the square root of 98. So these are not like radicals. The reason for that is, they're not the same radical. This is the square root of 72. This is the square root of a totally different number, 98. So I can't put these together like in examples 1 through 4. So we have to simplify radicals first, if possible. So we simplify radicals first, and then add or subtract any like terms with like radicals. Okay, so the square root of 72, remember this is a square root, so I'm looking for factors that are of 72 that are a perfect square. Well, this is the square, using the product rule for radicals, this is the same thing as the square root of 36, which is a perfect square, right? That's 6 squared, times the square root of 2. Alright, so the square root of 72 I can rewrite as 6 times the square root of 2. And then same thing for the square root of 98. Right, the square root of 98, I can break this up using the product property. That's the square root of 49 times the square root of 2. And the square root of 49 is 7. And so this is 7 times the square root of 2. Now, look, we have like radicals. All right. Both terms now will have the square root of 2 involved. Alright, so starting with this, we simplify each radical. Pardon me. Square root of 72 we said was 6 times the square root of 2 minus, right, we're subtracting, and the square root of 98 we said was 7 times the square root of 2. Now we have like radicals, and we can put them together. So remember, you just do 6 minus 7, which is negative 1, times the square root of 2. Right? It's, again, I'm not going to do the factoring thing anymore here. You would factor out the square root of 2, and then again 6 minus 7 would be left over, which is negative 1, which you can just express with a minus sign. And there we go. That's as simple as that gets, right? And you could, if you wanted, just let me show you this. I'll pull up a calculator, and we'll demonstrate that these indeed, the expression I started with and the expression I finished with are the same number. And you can do this all the time if you wish. All right. So what I have here is a TI-84 Plus simulator. All right. And again, you can use any calculator you want to check this out, test your results. So the expression I started with was, the square root of 72, then minus the square root of 98. And you're seeing we get negative 1.4142135562, etc. Right? Now I'm going to enter the expression we ended up with, right? This negative square root of 2. And it should be the same thing, right? Negative square root of 2. And it is indeed the same number. Alright, so we did a good job. Right. Okay. So part B, same thing, but this time they're cube roots, and they're starting off not like, right? We have the cube root of 24, and this radical in this term is a totally different radical. Right? It's not the cube root of 24, it's the cube root of 81. So if that's the case, we need to simplify radicals first and then add any terms with like radicals. Alright, so off to the side here, let me just make a little separation here. Now the cube root of 24, right, you have to think of what are factors of 24 that are perfect cubes, right? Perfect third powers. Well, 8 is a 2 to the third, right? 8 is a perfect cube, so I can break this, and it goes into 24 evenly. I can break this up using the product property as the cube root of 8 times the cube root of 3, which, the cube root of 8 is 2. So this is 2 times the cube root of 3. And the other term has a cube root of 81. Again, you think, what's a perfect cube that goes into 81? Well, 81 is 3 to the 4th, so definitely 3 to the 3rd, or 27, goes into 81. You can break this up to the cube root of 27 times the cube root of 3. And the cube root of 27 is 3. Right, so this is 3 times the cube root of 3. And after simplifying, you see, oh, I have like radicals now, right? Both of these have the cube root of 3, the same radical. So rewriting the terms, the cube root of 24 is 2 times the cube root of 3 plus the cube root of 81 is 3 times the cube root of 3. And then you could factor the cube root of 3 out. Right, so you'd have the cube root of 3 at the end, and the other factor left over would be 2 plus 3, which would be 5. Right? So this ends up being equivalent to 5 times the cube root of 3. Right? And that's it. And once again, you could go to a calculator, which I won't do this time, but punch this original expression into a calculator, punch this last expression in, and you'll see that they are indeed the same number. Alright, then part C has fourth roots. So we're looking for factors of the radicand that are perfect fourth powers. Right. Okay. So we have 1/2 times the fourth root of 80 minus 2/3 times the fourth root of 405. These are not like radicals. Right? Yeah, they're both fourth roots, but they're not fourth roots of the same thing. Right? So I can't put these together right now. So off to the side, I'm going to simplify the radicals. Right? The fourth root of 80, right? Now remember, it's a fourth root, so I'm looking for perfect fourth powers. Now 16 goes into 80 evenly, and 16 is 2 to the 4th power. So I can break this up as the fourth root of 16 multiplied by the fourth root of 5. Right? 16 times 5 is 80. And the fourth root of 16 is 2. Right? So we have 2 times the fourth root of 5, right, for the fourth root of 80. Right? And then the other fourth root, the other radical, the fourth root of 405, well, this is 5 times 81. 81, as I said earlier, is 3 to the 4th power. 81 is a perfect 4th power. So I can break this up to the fourth root of 81 times the fourth root of 5. And the fourth root of 81 is 3. Right, so this ends up being 3 times the fourth root of 5. And look, now we have like radicals. Both will have the fourth root of 5 in them. Alright, so putting these in, we have 1/2 times, the fourth root of 80, we said was 2 times the fourth root of 5. minus and then 2/3 times the 4th root of 405 was 3 times the 4th root of 5. All right, and then simplifying the products here, half of 2 is 1. So this first term is really just 1 times the 4th root of 5. Then we have minus, and then 2/3 times 3. The 3's would cancel. I'd be left with 2 times the 4th root of 5. And then finally, these have like radicals, both these terms, right? The 4th root of 5. So I'll factor the 4th root of 5 out, right? So I'll have the 4th root of 5 as one factor, and then the other factor will be 1 minus 2, which is -1. So I can just represent that by a minus sign in front of the 4th root of 5 there. And there we go. That should be good. And again, we can enter this into a calculator, the original expression, enter the final expression into the calculator as well, and you should get the same result. Great. Now every question from here on out, and I've got a few more. We're going through eight examples, I think. No, I have 9 examples, 9 questions. Everything from here on out, we're going to be doing this, like in number 5, where it starts off where the radicals are not like, and we have to simplify them so that we get like radicals, and then we can add or subtract. All right, so question 6, which is exercise 176, part A. You have the square root of 45 plus the square root of 80. Alright, so once again, these are not like. So I'm going to do this off to the side. We'll simplify, right, each radical. The square root of 45 is the square root of 9. Right, that's a perfect square times the square root of 5. So that's 3 times the square root of 5. Alright, then the square root of 80, pardon me, is the square root of 16, which is a perfect square, times the square root of 5. And the square root of 16 is 4. Right? 4 squared is 16. So 4 times the square root of 5. And now I have like radicals, right? Both have the square root of 5. And we're adding them. Alright, this is 3 times the square root of 5. Plus 4 times the square root of 5. Factor the square root of 5 out. And then 3 plus 4 is 7. Right? The other factor would be 7. So we end up with 7 times the square root of 5 for our final result. All right. Okay, next question, part B, 6 part B. Cube roots this time. The cube root of 81. Again, they're not like, so I have to get them to be like. Well, we saw the cube root of 81 earlier, right? That's the cube root of 27, which is 3 cubed, times the cube root of 3. So this is 3 times the cube root of 3. And the cube root of 192, is the cube root of 64 times the cube root of 3. Right, 3 times 64 would be 192. And the cube root of 64 is 4. Right? 4 to the 3rd power is 64. So this is 4 times the cube root of 3. And now I have like radicals. Right? They both have the cube root of 3. So this is 3 times the cube root of 3 minus 4 times the cube root of 3. Putting these together, we get -1 times the cube root of 3. Right, and then I'll just put minus the cube root of 3. Okay. Great. All right, next, now we saw these in number 5, part C. All right, the fourth root of 80 and the fourth root of 405. It's just different fractions this time. So I'll just bring that up again, number 5, part C. That was this here. So remember, the fourth root of 80 is 2 times the fourth root of 5, and the fourth root of 405 is 3 times the fourth root of 5, right? So this here is 5 halves times 2 times the fourth root of 5 plus, and then we have 7/3 times, and then the fourth root of 405 is 3 times the fourth root of 5. Alright, so in this first term, the 2's cancel, and I have 5 times the fourth root of 5 plus, and then in the second term, the 3's cancel, and you got 7 times the fourth root of 5. And 5 plus 7 is 12, so this is 12 times the fourth root of 5. And that's it. Right? That's our simplified sum. Great. All right, moving on. So we're now we're on question 7, which corresponds to exercise 178. And same deal, but this time with variables involved. Right, the radicand now has variables. Right. But the same thing, part A, we have the square root of 48b to the 5th minus the square root of 75b to the 5th. And before I even get started here, remember, these are even roots. Square roots, even roots, square roots, fourth roots, sixth roots, etc. And if you recall, we're trying to deal with only real numbers right now. So we don't want the radicands to be negative. Right? Remember, the square root of a negative number is not real. Well, b to the 5th, I don't want these to be negative. I'll put that down here. Right, these are even roots. Even roots. We don't want negative radicands at the moment, right? Because the even root of a negative number is not real. Alright, so that leads me to the following statement. So in order for these radicands to be not negative, b has to be positive or greater than or equal to 0. Right. Because if b were less than 0, right, if b were negative, right, b to the 5th would also be negative, right? That's any negative number to an odd power would be negative. So that's why I'm saying this. Right. And because b is non-negative, we won't need absolute value symbols when we simplify this. I'll still put them at first, but then I'll write it without. Okay. So the radicals are not like, right? So we simplify. So I'll start off with the square root of 48b to the 5th. Right, we're looking for perfect squares, right? It's a square root. Now 16 is the largest perfect square, right? This is the square root of 16. And then b to the 5th, b to the 4th is a perfect square, right? Anything with a power that's a multiple of 2. So I can rewrite this as the square root of 16b to the 4th times the square root of 3b. Right, that's a 3b. And once again, b can't be negative because this wouldn't be a real number, and you can only use that product property when you're dealing with real numbers. And this would be, 4 times b squared, which I don't need absolute values around. Right? The square root of b to the fourth would be b squared, and again, we're saying that b is non-negative here. Don't need absolute values. So this is 4b squared times the square root of 3b. Alright, so that's the square root of 48b to the fifth, totally simplified. And we'll rewrite that in a second. Then the other radical, right, the square root of 75 b to the fifth, can break that up to the square root of 25b to the fourth, right, perfect squares, times the square root of 3b. Right. And the square root of 25b to the fourth would be 5b squared. And no need for absolute value symbols or anything because we're assuming b is non-negative. Also, it's b squared. That'll never be negative anyway for real number values of b, times the square root of 3b. And we're subtracting here, right? We have, so this is equal to 4b squared times the square root of 3b minus 5b squared times the square root of 3b. And now we have like radicals, right? They both have the square root of 3b in common. They also have b squared in common. So you could pull out b squared times the square root of 3b and then just do 4 minus 5 is negative 1. Right, put a minus sign in front. So negative 1b squared times the square root of 3b. And that would be, as simple as that gets. Right. Again, I'm trying my best to make my b's not look like a 6. Right. So that's negative b squared, not 6 squared, times the square root of 3b. Okay. And if you'd like to test it out, just replace b with any any non-negative number. Replace b with 1, with 2, with 5, whatever you want. That's not negative. And punch them into the calculator, this expression in the beginning and this expression at the end, and they should give you the same value, but I'm not going to do that. All right, I'll leave that to you. Okay, part B. Now this time we have odd roots. Pardon me. Odd roots. Right, cube root, fifth root, seventh root, etc. And remember, when you're doing odd roots, the radicand can be any real number you want. So I'm not going to put any, there are no restrictions on q here. In part A, b had to be non-negative for us to be able to still deal with real numbers. Here, q can be anything. Right? You can take the odd root of a positive number, a negative number, 0, doesn't matter. So there are no restrictions. Alright, so once again, off to the side, we have some non-like radicals. I want to simplify these. But now they're cube roots though. Alright, so we have the cube root of 64 q to the sixth. Well, 64 is 4 cubed. So this is 4, and then the cube root of q to the sixth would be q squared. Right? Remember, q squared to the third would be q to the sixth. And there's nothing left over in the radical, so this simplifies nicely, right? It's just 4q squared. And the cube root of 125 q to the sixth, again, is a nice perfect cube. The cube root of 125 is just 5, right? 5 to the third power is 125. And the cube root of q to the sixth is, again, q squared. So definitely like radicals because there aren't radicals anymore. Right? This ends up being a statement without radicals. So we have 8 times the cube root of 64q to the sixth is, again, 4q squared minus, and then next term, 3 times 5q squared. Right, don't forget the times symbol, right? Because you might accidentally write 84 and 35. This is 8 times 4 and 3 times 5. Now 8 times 4, that's 32 q squared, minus, and then 3 times 5, 15 q squared. And we have like terms though, right? We both have q squared you could factor out, and then 32 minus 15 is 17. Right? So this ends up being 17 q squared when all is said and done. Alright, and once again, I leave it to you to check. If you want to test this out, replace q with any number you want in the original expression and in this final expression, and they'll both give you the same result. Alright, so like if q were 1, the original expression and the final expression would both be equal to 17. Alright, and so on. I leave it to you to check. Great. Alright, so question 8. Same stuff, but this time both have even roots. Part A has square roots and part B has fourth roots. Alright. So we're going to have to really pay attention here. Alright, now notice again in part A we have even roots, square roots, and so I want the radicands to be non-negative. So d to the ninth, both of them have d to the ninth. So I can't replace d with a negative number, right? So d has to be non-negative once again. Right? The value I replace d with has to be greater than or equal to 0 in order for us to be able to continue on with this. Right? Because if d were negative, you'd be taking square roots of negative numbers in both of these radicals, and those would not be real. Alright, so just keep that in mind. And if that's the case, if we assume that d is greater than or equal to 0, then we don't need any absolute value symbols if they ever are necessary. They won't be needed because the variables aren't representing negative numbers anyway. Alright, then we simplify each radical here. Square root of 96 d to the ninth. I can break this up to the square root of 16 d to the 8th, right? Those are perfect squares, times the square root of 6d, right? 6 times 16 is 96, and d to the 8th times d would be d to the 9th. All right, now the square root of 16d to the 8th would be 4d to the 4th. Right, 4d to the 4th, and again, no need for absolute value symbols because we're assuming d is non-negative anyway. And even if you didn't assume d was non-negative, d to the 4th power, an even power, is not going to be negative, so you don't need absolute value symbols here. Times the square root of 6d. All right, so there's the square root of 96d to the 9th simplified. The other square root, the other radical, the square root of 24 d to the 9th. I'm going to break up to the square root of 4 d to the 8th, perfect squares, times the square root of 6d. And this would be, the square root of 4 d to the 8th would be 2 times d to the 4th times the square root of 6d. Right. Now we have like radicals, right? Both terms are going to have the square root of 6d. So we have 4 times d to the 4th times the square root of 6d minus, and then 2 times d to the 4th times the square root of 6d. And then we combine like terms, like radicals here, right? You could factor out the square root of 6d. You could also factor out d to the 4th, right? So I pull out, they both have d to the 4th times the square root of 6d in common. And then with just 4 minus 2, which is 2. So I end up with 2d to the 4th times the square root of 6d. And again, you want to double check. Just pick any value of d that's not negative. Plug it in the original expression, plug it in the final expression, and they should end up giving you the same result. Okay. All right, now this part B is a little different. Part B is a little different. In part A, you had d to the 9th in the radicand as a factor, so d couldn't be negative, because a negative number to an odd power would be negative again, right? You don't want to take even roots of negative numbers, and those aren't real. In part B, yes, there are even roots, right? Fourth roots. But look at the expressions inside, the radicands. You have 243 times s to the 6th. That's an even power. So this will never be negative for any real number value of s. Same thing with this one, 3s to the 6th. Those will never be negative, right? So s, in this case, can be any real number. You can plug in any real number you wish. But if that's the case, that means absolute values may be necessary. Remember, when simplifying even roots of variable expressions, the absolute value symbol may be necessary, because when you see the even root symbol, it's asking you for the principal even root, right? The non-negative even root. So absolute value symbols may be needed. Right, back here, when I said d couldn't be negative, you didn't need absolute value symbols. So, but if the variable here can be any real number, absolute value symbols may be needed. All right, so let's keep that in mind. All right, so once again we have non-like radicals. So I want to simplify them, right? So we have fourth root though, right? So we're looking for perfect fourth powers. So the fourth root of 243 s to the 6th, that'd be the fourth root of 81, that's 3 to the 4th, s to the 4th is a fourth power, times the fourth root of 3 s squared, right? 81s to the 4th times 3s squared would be 243s to the 6th. All right, and here's where the tricky part comes in, right? The fourth root of 81s to the 4th would be 3 times not just s, right? Not just s, because remember the fourth root of s to the 4th would be the absolute value of s. And the only reason I'm doing this is because s can be any real number. So if s were negative and I didn't have the absolute value symbols, this expression would be incorrect. This simplification would be wrong. So 3 times the absolute value of s times the fourth root of 3s squared. All right. And then the other radical, right, the fourth root of 3 times s to the 6th, I'd break up to the fourth root of s to the 4th, right, a perfect fourth power, times the fourth root of 3s squared. And as we just said, right, the fourth root of s to the 4th wouldn't just be s, because s can be any real number here. So if s were negative, that would be wrong, right? You have to do the absolute value of s. All right, so it's the absolute value of s times the fourth root of 3s squared. All right, and then putting these in, we have 5 times 3 times the absolute value of s times the fourth root of 3s squared plus, and then 2 times the absolute value of s times the fourth root of 3s squared. And 5 times 3 is 15. I'm just going to write that here. So we have 17. Both of these terms have the absolute value of s times the fourth root of 3s squared in common, so you could factor that out. You'd be left with 15 plus 2, or 17 for the other factor. So we have 17 times the absolute value of s times the fourth root of 3s squared. right? And this is as good as that gets. All right, and once again, you want to test it out. Replace s with any number you want, right? It can be any real number this time, because the radicands will never be negative, because you have s to the 6th power, right? Even power. And see if the value of the original expression is the value of the expression at the end. Now, in some homework exercises and whatnot, if they tell you to assume that all the variables represent positive numbers, which I've seen several texts that do that. So if you're not working in this OpenStax text but somewhere else. Now if you assume s is a non-negative number, right, if you assume s is not negative, then you can say this expression simplifies, this expression we started with simplifies then to 17 times s. You just don't, all that means is you just don't need the absolute value symbols anymore. So 17 times just s times the 4th root of 3s squared, right? And this would be your final result. All right. But that's a big if, right? That's a big if. Right. When I was working, when I'm working on these exercises here, they didn't say anything of the sort in the instructions. All right, let me go back to the book page. All right. See, it just says in the following exercises, simplify. All right, it says nothing about assuming the variables are representing positive numbers or non-negative numbers. All right. So just bear that in mind. Be careful. All right, and I have one last question. All right, number 9, which is representing, this is exercise 182. And, it's no different than anything else. It's just 3 terms. All right, it's just 3 terms. Once again, though, even roots, square roots. So I don't want the radicands to be negative. So I got 75y squared. Well, that'll never be negative because y is to the 2nd power. This radicand 48 is always 48, right? So that's not negative ever. And then same thing here, 300y squared. That's not negative either. So no matter what I plug in for y, we're good. Right? So y can be any real number. Right. Meaning that, as in the last example, right, that absolute value symbols might be necessary. All right. So off to the side here, we'll simplify each of these radicals first. Right? So the square root of 75y squared. I'm going to break that up to the square root of 25y squared, right? We're looking for perfect squares, times the square root of 3. Right? Now, remember, y can be any real number. It can be a positive number, it can be a negative number here, and we're totally fine. Right? We don't have any non-real. We can plug any number in for y in the original expression. So this is not just 5y, it's 5 times the absolute value of y. Right? If you put just 5y, that wouldn't be correct. Because if y were negative, that would be an incorrect simplification. So we have 5 times the absolute value of y times the square root of 3 for the square root of 75y squared. Then the square root of 48, right, looking for perfect squares, that'd be the square root of 16 times the square root of 3, and that's just 4 times the square root of 3. Right. But notice the like radical, square root of 3, square root of 3. Right. And then finally, this last radical, the square root of 300y squared, I can break up to the square root of 100y squared, right, perfect squares, times the square root of 3. And once again, this is 10, not y, right, not just y, because what if y were negative? You'd be wrong. it'd be 10 times the absolute value of y. Remember, this is the positive square root. Anytime you see an even root symbol, it's asking you for the positive one. So we have 10 times the absolute value of y times the square root of 3. Okay, and then putting these in to the expression, so we have 3 times, and then 5 times the absolute value of y times the square root of 3 plus 8y times 4 square roots of 3, right? Minus, and then 10 times the absolute value of y times the square root of 3. And notice every single one of these has a square root of 3 in common, right? Every single term has a square root of 3 in common, and I can just combine, I'll factor that out. Right, we have the square root of 3 pulled out, and what I'd have left over is 15 absolute value of y. This is 15 absolute values of y minus 10 times the absolute value of y over here, right? So that'd be 5 times the absolute value of y. Okay? Hopefully you follow me. 15 absolute value of y minus 10 absolute value of y makes 5 absolute value of y, and then we have plus 32y. Right, and you think, hey, these don't go together. Right, this has y, this has the absolute value of y. These are different. So if we say y can be any real number, this is as simple as this expression gets. Because again, you can't combine 5 times the absolute value of y with 32y. Because absolute value of y and y are different expressions. Okay. Now, most times though, they'll probably tell you, hey, don't worry about the absolute value symbols. In most books I've seen, for some reason, so if we assume, big if, right, if we assume that y represents some non-negative number, right, then this becomes 37y. Oops, sorry. 37, because this would just be 5 times y. There'd be no need for the absolute value symbols. You would have 5 times y plus 32 times y is 37y, and then times the square root of 3. Right. And this would be as simple as that gets. If we assume that y is non-negative. Right. Now you could also break this up into 2 parts. Remember how absolute value is defined? You go back to saying y can be any real number. If y is not negative, you got 37y times the square root of 3, right? Again, that's if y is greater than or equal to 0, like I said down here. Or, what if y were negative? Right? What if I replace y with a negative number? Remember, if y is negative, the absolute value of y is negative y. So this would be negative 5y plus 32y. That'd be 27y times the square root of 3. Alright, so you could say that as well, but again, most of the time they'll probably tell you to assume that the variable is a positive number. Just be careful though with even roots. Right? And you've seen this in previous videos of mine if you've been following, right? You got to pay attention to your even roots when simplifying, whether or not absolute value symbols will be necessary. Alright, and that's it. So I'm hoping that watching me go through these 9 problems here with all the different parts helps you in some way when you're asked to add or subtract radical expressions on your own. And thank you very much for watching.